Good afternoon, everyone. Thank you very much for listening to my talk. I'm very happy to talk here about confirming safety of IAM specification and their OSS implementation. Before my talk, let me introduce myself to you briefly. My name is Takashi Norimatsu. Working for Hitachi Limited, Japan, and I am also the Keycloak maintainer. Keycloak is identity and access management open source software. I have been Keycloak maintainer since October 2021, and I have been mainly contributing security features to Keycloak. So, in the first part of this talk, I'd like to talk about the theory regarding how to make the IAM OSS secure. And after that, I'd like to talk about the practice that follows the theory by picking up the Keycloak as its case study. And this talk is basically based on my research activities in my doctoral courses. And so therefore it includes a lot of references to peer-reviewed academic research papers. And also these presentation materials include some slides that might be difficult for me to describe shortly in this talk. So in this case, I will omit the description of such slide. So if you are interested in this topic, please refer to this slide afterwards. Maybe these slides have already been available from the Open Source Summit Europe official site. So for identity and access management, IAM, the open source software that provides authentication and authorization capabilities, I think there are three types of vulnerabilities that we need to identify and address. The first type is included in the specification itself, and the second type is included in the implementation of this specification, and the third type is included in implementation as a whole. In order to identify those vulnerabilities, we can take the following three measures respectively. Conducting formal security analysis for the first type of vulnerability, and running conformance testing to identify the second type of vulnerability, and running the vulnerability testing to identify third type of vulnerability. And of course, honestly speaking, to make our IAM OSS secure, so we need to consider the other points. For example, the supply chain, the security, and so on. But in this talk, I'd like to focus on the following vulnerabilities. So as just mentioned before, considering IAM OSS security, there are three types of vulnerabilities, and by applying the following three types of methods, we can identify those types of vulnerabilities. So first, I'd like to talk about formal security analysis to identify the vulnerabilities included in security specifications. So originally, formal method used by formal security analysis were applied to specification written in natural language and implementation of the specification. So it's difficult to verify that this implementation correctly implemented the specification because there is some ambiguity in natural language, and also it takes a lot of time. So therefore, a comprehensive human verification might be impossible. So by formalizing both specification and implementation onto some mathematical model, then it can be done because there is no ambiguity in mathematical model, and also we can run semi-automatically or semi-automatically verification method against those models. Therefore, by substituting specification with security requirements and implementation with specification, then we can, by using a formal method, it's possible to verify that the security specification satisfies the security requirements. So, in my opinion, there are two types of formal analysis method: model checker and theorem prover. Each has its own characteristics. So, regarding the model checker, we can generally semi-automatically run model checker, and it's good for discovering an actual attack method against the system. And the ProBelief is one of such a model checker. It converts the security requirements and the specification, and also attacker's capabilities onto some mathematical model. And after that, it tries to try to find out whether the critical event happens or not. If this critical event happens, then the system security impairs. So probably if you also can try to find out an actual path toward this critical event. And regarding the theorem prover, we can use this theorem prover manually or interactively, and it's good for proving the specification is secure. Game hopping method is one of such theorem prover method, and easy crypt is one of such an implementation of game hopping method. This game hopping method converts security requirements and specification onto some mathematical game model, and it defined the safety as follows: the probability of an attacker beating a challenger in the game is negligible. In this case, the challenger indicates the people who define the specification by following security requirements. This slide shows how this game hopping method works. As just mentioned before, it converts security requirements and specification onto some mathematical game model in this slide number 0. And it requires us to prove its safety by ourselves manually. If this model is too much difficult to solve, to prove, Then this method convert this model onto the more simplified model in this slide number 1. By repeating this process, we can finally reach out the simplest model in this slide number n, model number n. Then after the proving this model security by ourselves, this method the trace back onto the original model to show that the original model number zeros is secure by applying the SMD solver, satisfiability modulo theorem solver. So this is how this gaming hopping method works briefly. So I think the theoretical speaking, by conducting formal security analysis against the specifications, we can identify the vulnerabilities included in the specification. But in practice, there are some issues. I think the formal security analysis is not so usually used because it takes a lot of time and cost, and also it requires the special knowledge and expertise. So therefore, formal method is usually applied to the mission critical systems like aerospace or automobile industries. And also, the more complex the specification is, and the more difficult it becomes to apply the formal method. The next, I'd like to talk about the conformance testing to identify the vulnerabilities included in the implementation of the specification. Before considering the conformance testing, I would like to consider other options to identify such vulnerabilities. A formal method and code review as heuristic static method. Formal method, as just briefly mentioned before, formal methods can also be used to apply for the specification and its implementation. And this slide shows one of such an formal method applying to specification and implementation. And so it converts the specification and implementation onto some kind of formal first order predicate eventually, and it tries to solve this predicate by applying SMD solver by treating this predicate as the satisfiability problem. So regarding code review, as you may know, the human reviewer review the implementation of the specification. So, but in nowadays, AI is the hot topic. So therefore, I briefly considered whether we can leverage LLM for this purpose, namely the code review. There are several research papers regarding this topic. Some of them used LLM as a reviewer of the implementation, while others used LLM as evaluator of the reviewers' review result. So regarding the conformance testing, before talking about conformance testing, I would like to define conformance testing in this talk as follows: the verifying the program implementing the specification actually complies with the specification. And I think there are two types of conformance testing: publicly available and publicly unavailable. So there are several conformance testing program suites in the world. I'd like to introduce to you some of them. OpenID Foundation, the standardization organization for digital identity specification, publishes the official conformance suite for OpenID Connect, OIDC, and FAPI, Financial Grade API Security Profile specification. And regarding OAuth 2.0, some research activities published the conformance suite named OAuth or OAuth. And Healthy ID is a national authentication service for healthcare industry in Norway. Healthy ID also publishes the official conformance test program suite. Then, so all of those conformance testing program suite applied the black box testing strategy, which means that maybe they created the test cases by reading the specifications, maybe manually, and they run its implementation and send a request, including the input of the test cases, and observe its response as an output of the implementation. Then it compare this output with the expected output of the test cases. Also, I briefly consider whether we can leverage AI or LLM for the conformance testing. There are several research papers regarding this topic. Some of them used LLM as a generator of test cases, while the others used LLM as an evaluator of those test cases. So, by theoretically speaking, by running conformance testing, we can identify the vulnerabilities included in the implementation of the specification. But in practice, I think there are some issues. As just mentioned in the formal security analysis, applying formal method might be difficult for the people who are not familiar with this topic, and also it takes a lot of time and cost. So therefore, I think the black box testing style conformance testing is usually used. And in my opinion, the LLM leveraging conformance testing is not so yet mature. So there is some room to do a lot of research on that topic. So next, I'd like to talk about vulnerability testing to identify the implementation as a whole. When we consider IAM, open source software, we need to not only implement the specification, but also we need to implement the other part, other software. So therefore, we need to identify the vulnerability and address those kind of vulnerabilities included in the implementation as a whole. Before talking about vulnerability testing, I'd like to define it as follows in this talk. identify security weakness that can be exploited by an attacker. And I think there are two types of vulnerabilities, known and unknown, or zero-day vulnerability. Most of the research papers I investigated took the following two basic configurations for vulnerability testing. One is for web application, and the other is for mobile application. Both include the entity, the IDP, identity provider, and RP, reliant party, and user and the browser. And so they usually used the following three methods: the black box and white box and hybrid. The black box testing method is to capture, record, modify, insert, delete, out of order sending the messages communicated among each entities in the configuration. While white box testing is to investigate the source code of IDP and RP. And hybrid testing is the combination of black box and white box test. The most of the research papers I investigated used the attacker model defined by the OSS security best current practice, and they used the threat model defined by the RFC 6819 of two threat model and security consideration. They usually took the two basic strategies for vulnerability testing. The first strategy is to create a finite state transition model (FSM) that represents the system, while second strategy is to find heuristically the way of exploiting known vulnerability. The first strategy takes the following two sub-strategies, each for detecting known vulnerability and unknown vulnerability. Regarding detecting known vulnerabilities, they incorporated the mitigation of the known vulnerabilities and/or security properties of the system to the FSM. And they actually sent a message to the real system that causes the state transition of the system and observed its response to and inferred the state of the system. And finally, they matched the inferred state with the expected one from the FSM. If not matched, they concluded that some vulnerabilities are included in the system. Regarding the detecting unknown vulnerabilities, they analyzed the FSM to find a way of an assumed threat by an assumed attacker model. So most of the research papers are investigated for vulnerability testing using the black box testing method developed a plugin of the browser or a proxy by themselves to control the message exchange between the entities in the system. And to create an FSM, they took the following method from the specification, namely by reading and interpreting the specification, or observing the system, which means observing the message communicated in the real system to construct an FSM. And some of the research papers tried to refine this FSM by applying the method called fuzzing. The fuzzing means that it slightly modifies a captured message, send it to the system, and observe its response to gain the more detailed information about the system or underlying security protocols. Regarding white box and hybrid testing, the most of the research papers I investigated usually targeted Android application. Then they took the following two methods. The first, they represent the system and security properties as certain type of a graph like a tree. After that, they solved the formalized problem by applying the method depending on the type of the representation. And regarding only the hybrid testing method, they usually used the black box testing method for constructing the FSM. And after that, they use white box test method to refine the FSM model. So theoretically speaking, by running vulnerability testing, we can identify the vulnerabilities included in the implementation as a whole. But I think there are some issues in practice. So applying the testing method I described just before in the research papers may be difficult for a developer who are not familiar with this research area. And regarding the detecting unknown vulnerabilities, I think it seems there are suitable representations of the system for that purpose. In this case, the FSM or intermediate model that can be analyzed by formal analysis and so on. So by applying the three methods I just described before to identify vulnerabilities, we can assure that we can make sure our IAM is secure. But as time flies and technology advances, some new vulnerabilities may come into our OSS. So therefore, we need to do some kind of the activities for maintaining the OSS, the product security, in its lifetime. So in the first of this talk, I mainly described the theory regarding how to make an OSS secure. In the last part of this talk, I'd like to talk about the practice that follows the theory by picking up a Keycloak IAM OSS as its case study. Keycloak is identity and access management of the software that can provide authentication and authorization features. And it complies with several open security specifications for authentication and authorization. And Keycloak has been a cloud-native computing foundation's incubating project since 2023 April. So first, I'd like to talk about the specification that Keycloak supported and its formal security analysis result. Keycloak supported the following the security specifications, and the research institute conducted formal security analysis against those security specifications. In this talk, I'd like to talk about the following security specification and its formal security analysis. Regarding the OAuth, some research institute conducted formal security analysis against not only OAuth 2.0 but also its extension. They found several vulnerabilities. But I'm not sure whether they contacted the standardization organization. In this case, the IETF. So regarding the OIDC, OpenID Connect, some research institute conducted formal security analysis against OIDC and its extension, its extension specification. And they found some vulnerabilities. They contacted to the standardization organization, in this case OpenID Foundation. Then, by receiving the feedback, the OpenID Foundation successfully fixed the specification. So therefore, in this case, the formal security analysis has been actually contributed to make those specifications more secure. Regarding FAPI, financial grade API security profiles, maybe you might not hear the word FAPI, so I'd like to briefly describe it. FAPI is the financial grade API security profile, sometimes called FAPI, and it's enhancement of OAuth 2.0 specification, and defined by OpenID Foundation. The main objective of FAPI is to harden the security aspect provided by OAuth 2. So therefore, the FAPI is intended to be used by the systems that require high security level. For example, the system providing the financial services to the end user via APIs. In this case, the FAPI is used. Now, actually, there are some such kind of system in the world. For example, in United Kingdom, the UK Open Banking, and in Brazil, Open Finance Brazil, or formerly Open Banking Brazil, and in Australia, Australia Consumer Data Rights. The ecosystem adopted these FAPI specifications. Then, some research institute conducted formal security analysis against FAPI specifications, and they found several vulnerabilities. So they contacted to the standardization organization, in this case the OpenID Foundation. By receiving the feedback, the OpenID Foundation fixed the FAPI specifications vulnerability. So therefore, in this case also, the formal security analysis actually contributed to make those specifications secure. So next, I'd like to talk about the conformance testing in Keycloak project. So there are, regarding the conformance testing, there are the three types of the situations. Sometimes we cannot get an official conformance test. In this case, in Keycloak project, the Keycloak contributor need to write the self-integration test by themselves. We call this situation the past integration test. And sometimes we can get the official conformance test from the standardization organization. In this case, the Keycloak project ran this conformance test against the Keycloak to confirm that Keycloak passed this conformance test. We call this situation the past conformance test. And some standardization organization provide official certificate program, which certifies the software product comply with the security specification. So, for example, the FIDO Alliance and the OpenID Foundation provide this certificate program. And Keycloak got certified as the software product comply with several security specifications by OpenID Foundation. So we call this situation the certified. So the certified situation is the highest level of assurance of the conformity, while only the situation where only past integration test is the lowest level of assurance of conformity. These slides and the following 2 or 3 slides list all of the specifications Keycloak supported, and also whether those security specification got certified or pass conformance test or only pass self-integration test. It has a lot of the specification, therefore in this talk I'd like to skip the descriptions. So if you are interested in this topic, please refer to this slide afterwards. So as just mentioned before, AI is very hot topic. So some of the Keycloak contributors, including me, have been trying to support AI-related specification. In this slide shows the MCP, Model Context Protocol, trying to use Keycloak as authorization server in MCP. I would like to briefly mention that point because AI is a hot topic. And so currently there are the 3 Keycloak official special interest group, OAuth SIG and SRE SIG, Site Reliability Engineering SIG, and AI SIG, official 3 SIG. And the Keycloak, the OAuth SIG, developed the automated conformance test run environment for running the multiple OpenID Foundation's conformance test simultaneously and automatically. So by using this environment, the Keycloak project ensures that every version of Keycloak, not only major but also minor and micro version, every version of Keycloak complies with the specification that older versions have already supported. And next, I'd like to talk about vulnerability testing in Keycloak project. Keycloak project uses the following 4 tools: the CodeQL for Keycloak source code, and Dependabot for Keycloak dependency packages, and Treebees for Keycloak container image, and Sync for Keycloak container image and Keycloak's Kubernetes operator. And finally, I'd like to talk about how Keycloak project maintain the project security. The Keycloak project adapt the OpenSSL scoreboard to assess its security risk management. The Keycloak project has been taking several measures to achieve this scoreboard score. And the current score is 9.3. Maybe I think the Keycloak project has been well managing its security risk at this time. Also, Keycloak project established the security policy and security charter, and namely how we maintainer and also Keycloak development team respond to security reports from the Keycloak users. And the Keycloak have taken several security audits conducted by external specialist agencies. You can see the result publicly. And as just briefly mentioned before, the Keycloak project used the following tools for vulnerability testing and management. And the Keycloak project established the Keycloak security advisories for publishing vulnerability information and treatment, and also secure software development life cycle. Before moving to my talk's conclusion, I'd like to mention one point. If your system uses Keycloak, then I recommend you to run conformance and vulnerability tests against your system using the Keycloak. Because I'd say that the Keycloak project run conformance tests, vulnerability tests against Keycloak. But however, the setting of the Keycloak may be different from the one of your system. So therefore, I recommend that point. Sometimes I heard the question. In this talk, in the first of this talk, I mainly talked about how to make the IAM OSS secure in theoretical part, as a theoretical part. There are 4 points: formal security analysis, conformance testing, vulnerability testing, maintaining product security in its life cycle. And in the last part of this talk, by picking up the Keycloak, I described how the Keycloak project do as a practice by following the theory. So that's all for my talk. Thank you very much. Maybe 1 minute over for this talk. So hopefully, if you are interested in these topics, please feel free to ask me in the venue. Thank you very much for your listening.